Today I'm going to teach you about numerical integration. So if you haven't done so already, go to my website and print out these notes so you can follow along. The question for today is, how can we compute areas such as the area under the curve y equals e to the negative x squared from a to b, or sine x squared from a to b? The problem with these functions is that they have no antiderivative. So we can't just take the antiderivative and plug in a and b and subtract. Instead, we have to compute these areas with a numerical estimate. So the answer is, what we're going to do is divide the interval from a to b into equal subintervals, each of length delta x, which is the length of the interval, b minus a, divided by n, how many intervals there are. And we're going to call the endpoints x0 through xn, and we're going to choose one of 5 ways to estimate the area geometrically. So the first way is called the left endpoint rule, and it means that we are doing this. Suppose here's our function, and we're going from a to b. We want to find the area. We're going to call a x0 and let's say b x4. So here we'll take n to be 4. We're going to evenly divide our interval from a to b into 4 sections. 4 intervals from a to x1, x1 to x2, x2 to x3, and x3 to x4. And we're going to do various things. So for the left endpoint rule, we're going to cut up our curve like this, and for each of these segments, take the left endpoint. So take the left side, the a as opposed to the x1 for this region, and we're going to extend it this way. So again, for the next one we take x1 and we extend it this way. For x2 we pick this point and extend it this way, and for x3 we pick the left side and we extend it this way, and we make rectangles. Let's close up these rectangles. So you can see we have chosen 4 rectangles, and we've chosen the left side as opposed to the right side of each rectangle to determine the height of each rectangle. Now, on this picture, delta x, by the way, which we said is b minus a over n, the length of the interval divided by the number of intervals, is just the width of each rectangle. So this width is delta x, and it's the same for each rectangle. So if we want to calculate the area here, I give you a formula to do that, but just so you know where the formula comes from, let's calculate the area of this first rectangle. That would be base times height. The base is delta x, and the height is this point, which is the function value at x0. It's the height of the graph. So the area of this rectangle is delta x times f of x0. That says delta x times f of x0 if you can't read it. And similarly, the area of the second rectangle would be delta x times f of x1, because the height is this, which is the height of the graph, the function value at x1. So you have delta x times f of x0 plus delta x times f of x1, etc. And that's this formula when you factor out the delta x. Notice that here the subscripts go from 0 to 1, 2, 3, all the way to n minus 1. So you don't actually go to x4. Here you would stop at x3. Now, for the right endpoint rule, you make basically the same graph, except with one difference. So the one difference is that instead of taking the left side of each of these regions, you start at the right side and go like this. So you make rectangles this way. And you can convince yourself that this is the proper formula to encapsulate this situation, where here the indices go from x1 through xn and don't include x0, because that first endpoint is not involved. go to the next page. To talk about some more accurate estimates, the trapezoid rule does something a little bit different, which is it estimates the area from A to B using trapezoids. So let's draw the same situation and pick these points, except now we're going to connect the points to each other to make trapezoid-shaped regions like this one. And notice all four of these are trapezoids. If you actually bother to make the calculation based on the area of a trapezoid formula, you will find that this is the correct formula. You get a delta x divided by 2, and then the pattern here is that you get 1 f of x0. So this point is counted once. And then the rest are all 2's. 2, 2, 2, 2, 2, 2, until the last one, f of xn, which is again a 1. So the pattern here goes 1, 2, 2, 2, 2, 2, 2, and then 1. And you can figure that out yourself or consult any textbook for the derivation of that. Slightly more accurate than the trapezoid rule is the midpoint rule, which does something a little bit different. Goes like this, to go from A to B on, let's say, this curve. Let's put in all our values on the x-axis from before. We're going to take the midpoint of each of these subintervals and go up. And at that point, we're going to go out to the left and right to make a rectangle. So we get this rectangle. So it'll be more clear on this one. We'll go to the midpoint and then go to the left and the right to make a rectangle. Here we'll go to the midpoint and then go to the left and to the right and complete the rectangle. That's the midpoint rule, and you can convince yourself that this is the proper formula for the midpoint rule, where putting a bar over xi means the midpoint of that subinterval. The last rule is the most accurate and the most complicated. It's called Simpson's rule, and it uses parabolas. And for this rule, n must be even, an even number. Now in this case, the cases I've drawn, n is 4, so we're okay. So let's draw this Simpson's rule picture. Again, we'll draw our curve from A to B. A will be x0, B will be x4. And what we're going to do is each pair of regions here, to figure that out, we will instead put a parabola through these 3 points. Like, let's say the parabola through these points looks like this. And because a parabola is a simple enough shape and has a simple enough equation, we can compute the area of the parabola through these 3 points pretty easily. Then we'll take the next 3 points, this, this, and this, and put a parabola through there and compute the area under that parabola. And it turns out this is pretty accurate. And it's pretty simple to derive this formula. Just look it up in your textbook or any textbook or online for where this comes from. If you make the calculation, you get this funny pattern where you get delta x over 3, and then you get f of x0, f of x1, f of x2, just like in all of these formulas, except the pattern of coefficients goes 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, and then the last one is 1 again. So it always starts with a 4 and ends with a 4, but alternates with 2's in between, and then has 1's on the ends. So let's do an example of a problem you can do with all these formulas. Go to the next page, and the first example is what if you had to estimate the natural log of 5 without a calculator? Something you could do is do this integral, because the antiderivative of 1 over x is natural log x, so you get natural log 5 minus natural log 1, and since natural log 1 is 0, the answer to this question is ln 5. If you didn't have a calculator, you couldn't just type that into a calculator. You'd have to estimate this using one of these numerical rules. So let's do this using the midpoint rule with n equals 8. Now my advice for all of these problems is draw the picture. I'm not sure why many students are very opposed to drawing a picture and just trying to jump straight to a formula, but most people who do that end up getting it wrong. And the time that you invest in drawing the picture will pay dividends in how correct and how fast writing down the formula is. So let's take the time to draw the picture. Your graph is of y equals 1 over x, which looks like that. So this is like f of x equals 1 over x. And you want to go from 1 to 5. X goes from 1 to 5. And we want n equals 8 with the midpoint rule. So we want 8 little rectangles. So if we're going from 1 to 5, we have to distribute that distance 4 units evenly over 8 rectangles. Each one must be 4/8 or 1/2. So let's mark all of those subintervals. Here's our delta x of 1/2, and indeed we get 8 subintervals. 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3, etc. We get 8 subintervals. So let's use the midpoint rule now. And so we go to the midpoint of each subinterval and we go up, mark a point, and then make it into a rectangle. So we take the midpoint here, go up, mark a point, and make it into a rectangle. Take the midpoint, go up, make a rectangle. And if we do that for all of these intervals, we get this nice picture. Now we can jump to the formula. And the formula on the previous page says, if I can find it here, m with 8 rectangles is delta x times f of x1, x2, all the midpoints of these intervals. So let's do that. M8 is delta x, which in this picture you can clearly see is a half, times f of the midpoints. Now from the picture you see the midpoint here is 1.25, halfway between 1 and 1.5. The next midpoint is at 1.75, halfway between 1.5 and 2. So 1.75. And you can see you do that all the way till the last midpoint, which is at 4.75. And now we just have to figure out what this is. So f of 1.25, well, f of x is 1 over x. So f of 1.25 is 1 over 1.25. Similarly, f of 1.75 is 1 over 1.75. So we get this. Now, if you type this into a calculator, which I did 5 minutes ago on my own, I get this, 1.5998. And you could do this on some cheap calculator that you got for free. You don't need a fancy calculator with a natural log button. And you've gotten a pretty good estimate of the natural log of 5. So the actual natural log of 5, by the way, is about 1.61. And we've got 1.60, basically. So we're about 100th away from the actual value. Not bad. So the next thing you can do with these numerical estimates of integrals, and a lot of the problems surrounding them involve error and how far off you are from the actual value. So if you want to know how accurate these estimates are, we have some formulas that will tell you how accurate your estimates are in the worst case. Note that we define error by actual area equals approximation plus error. So if the actual area is 2.30, but the estimate gives 2.32, the error is negative 0.02. So if we call the errors in the left endpoint rule EL and the error in the right endpoint rule ER, etc., here are the formulas that give the maximum possible errors on the next page. Here they are. Notice that they're all in absolute value, so the formulas don't distinguish between positive and negative errors. And they say that the actual that the error is at most k, some constant, which depends on the size of the derivative or second derivative or something on the interval. These should be commas, by the way. They depend on a k, also the size of the interval, b minus a, squared or cubed or something. And they also depend on n, the number of rectangles. So the tip for problems involving these error bounds is to find the value of k first. That often turns out to be the trickiest part. Sometimes you have to use the triangle inequality to find a suitable k. And this is the triangle inequality. It says absolute value of p plus q or p minus q is less than or equal to the absolute value of p plus the absolute value of q. Notice whether this is a plus or a minus, that's always a plus. And you can think about why it's called the triangle inequality. Although for our purposes it doesn't matter. It's just a useful fact to know. So let's do an example. How accurate was your estimate in number 1, the estimate we did of the natural log of 5? So we actually know that we're off by only 100th, but suppose we didn't have a calculator, you just computed 1.5998 and you want to know how accurate you are. Let's use one of these formulas. What was the maximum possible error in estimating this integral using the midpoint rule with n equals 8? So use the tip. Find the k first. With the midpoint rule, the k depends on the second derivative, f double prime of x. And it turns out absolute value of f double prime of x has to be less than whatever k we choose. We have to choose a k that's at least as big as f double prime of x. So let's see. If f of x is 1 over x, then f prime of x is negative 1 over x squared. And so f double prime of x is 2 over x cubed. So our k depends on absolute value of f double prime of x. So what is that? That's absolute value of 2 over x cubed. Now we need to choose a number that's definitely bigger than the biggest that this ever gets on the interval from 1 to 5. So if x is a large number, this denominator will be large, making this fraction small. So if we want this fraction to be large, we have to choose the smallest possible value for x, which on this interval is 1. So this is less than or equal to 2 over 1 cubed. And at this point you should convince yourself that if x is between 1 and 5, 2 over x cubed is always less than or equal to 2 over 1 cubed, which is 2. So if we need k to be at least as big as this, we can take k equals 2. At this point, now that you found the k, this problem becomes completely easy. Just write down the formula from higher up on the page. We have k times b minus a cubed over 24n squared, which is 2 times 64 over 24 times 64. Well, that's lucky. We get 1/12. So it means that even in the worst possible case, we are no more than 1/12 away from the correct answer when we said 1.5998. Let's do one more example here. And this problem is very important because it illustrates a couple of tricky points. This question is asking what value of n, how many rectangles, or in this case, how many trapezoids, do you need to find some integral to within 0.001 of the actual value using the trapezoid rule. So let's do it. And I'll point out the two tricky points along the way. So let's first look at the formula we need for the trapezoid rule for the error bound. For the trapezoid rule, where is it? There it is. For the trapezoid rule, we want k, and k depends on f double prime of x. So let's first find f double prime of x. If f of x is 2 minus x plus x cubed minus x to the fourth over 6, then f prime of x is negative 1 plus 3x squared minus 2x cubed over 3, and f double prime of x is 6x minus 2x squared. Okay. Now, we want a number that's at least as big as the biggest this ever gets. So f double prime of x in absolute value is this thing. Now we have to think about what's the biggest this quantity, absolute value of 6x minus 2x squared. What's the biggest that this ever gets on the interval from x equals 0 to x equals 3? And this is a little tricky of a problem. It's not as simple as the previous example, 2 over x cubed. So it's actually kind of hard to figure this out without taking a few minutes. So we're going to take a shortcut. This is sort of a quick and dirty shortcut using the triangle inequality. This was the tip from the previous page. We're going to break up this absolute value as the absolute value of the first thing plus the absolute value of the second thing. And when you do that, you have to put a less than or equal to sign. So we get this. This is much easier to think about. What's the biggest that this quantity ever gets from x equals 0 to 3? 6x from x equals 0 to 3, the biggest it ever gets is when x is 3. And similarly, for 2x squared, the biggest that this ever gets is when x is 3. And so that is 18 plus 18, so we get 36. So we can take k to be 36. And we can now guarantee that this second derivative is definitely no bigger than 36 on this interval. Now, there might have been a better value than 36, but we would have had to take some real care to find that. So this is perfectly acceptable for this kind of question. Just use the triangle inequality here to break up this into these two pieces, and then do each of these simpler pieces separately. Now we have to do, so that's the first tricky part, using triangle inequality. The second thing is we have to find what value of n we need. So if we go to our formula here, we see that the error is at most k times b minus a cubed over 12n squared. So our error is at most k times b minus a cubed over 12n squared. Now, at this point, many people would put the 0.001 over here on the left side, because it looks like that's where it belongs in the formula. But that doesn't make sense if you think about what the formula says. The formula is saying that the maximum the error could possibly be is this right-hand quantity. So if we want the error to be no larger than, let's say, 0.001, we want the biggest it could ever be to be less than 0.001. So this is a little bit tricky. Many people, again, want to put this 0.001 on the left side. But in fact, if you think about it, this is what makes sense. The error is less than 0.01, not 0.01 is less than the error. That doesn't make sense. We don't want the error to be greater than 0.01. We want it to be less than 0.001. So be careful about where you put the inequality sign here. This is the correct way to do it. Now at this point we just have to solve this. So my advice for solving this is to convert this decimal into a fraction. Let's see, this says 36 times 27. This as a fraction is 1/1000th. When you convert it to a fraction, you can now just cross multiply, and you can all do that. Let's actually simplify this first. 36/12 becomes 3. So I get 81 times 1,000 is less than n squared times 1, n squared. So n is bigger than the square root of 81,000, which is 284.6 approximately. So we need at least 285 trapezoids. And that's our answer. At this point, you're ready to just do a couple of problems yourself, so I suggest trying these two. And after you finish these two, if you're happy with your results and you think you did them right, you're then ready to do the homework on this topic.